What we're going to do in this short video is have a conversation about the physics of bodies on inclined planes. Now, it often happens in everyday life that you've got a body which is on an inclined plane. A common example of this is a car which is on a road which is inclined, a road which is down the side of a hill. What would happen is that car, typically if it was left to its own devices, it might actually begin to roll down the hill. You could have any kind of surface with any kind of body, a marble which is on a table which is not horizontal, any kind of surface, any kind of body, and what it works out to is something which looks similar to what we've got in this diagram in front of us. A body of mass m which rests on an inclined plane, and the angle of inclination in this case is given by theta. This is the angle which the plane makes with the horizontal. We may be asked to draw a free body diagram for this object of mass m, and that would be just a diagram where instead of us having the physical object, we've just got a dot, and then what we have is mass m next to it, and that could be a free body diagram or the beginnings of the free body diagram. So coming back to our physical diagram over here, we know that there is a force which acts on this body due to gravity, and that is the weight, and the weight acts vertically downwards, and there it is. We'll use the typical symbol, which is W. Now the weight acts downwards, and you can imagine that part of that weight is pulling that mass down against the plane itself. And part of that weight is helping that mass to slide down the plane. And from there, what we're going to do is we're going to split that weight into two components. Typically, when we deal with examples like this, we will imagine that the surface itself, that is this surface, is smooth, so friction doesn't come into play. But that doesn't change this part of what we're talking about, which is drawing the forces which act on that mass. If the weight acts in the direction shown, which is vertically downwards, there's a part of the weight which we can draw in this direction at right angles to the plane. Then there's a part of the weight which is going to be drawn parallel to the plane. What that looks like is there is this component here which makes a right angle with the plane, which pulls the body down into the plane. And then there's also another component which acts along the plane. But instead of drawing that component here at the level of the plane, I'm going to draw it over here. Okay. So there's this component at right angles to the plane and this component which is in the direction of the plane. And of course, if we use a little bit of simple trigonometry, then we'll see that this angle theta there is equal to that angle. So we can write theta into that. And in order to work that out, we can just draw that diagram on the side over here, just so that you're clear about how we ended up knowing that this angle there was theta. Just so that you are clear in terms of how we ended up knowing that that angle there is theta. What we have is we have the horizontal, and then we've got the plane. And we are at this point in the plane, and then we draw a line which is at right angles to the plane, that line over there. And then we have this line which is vertical. So if we complete this little triangle, then what we have is we have got that. So it then follows that this angle being theta, that being 90, that angle there is such that when you add that angle to that angle and to 90, you should get 180. So this angle, which I'll call alpha, can be represented as 90 plus theta plus alpha is equal to 180. Which means that alpha is equal to 180 minus 90 minus theta. 180 minus 90 is 90. So what we have is that alpha is equal to 90 minus theta. So alpha is 90 minus theta, and this whole angle there, if that is 90, that whole angle there is 90 degrees. then it means that this angle here must be theta. Stop the video for a moment and think about that explanation. Play it again if you need to, and we'll come back to the question in one moment. So coming back to the question, we don't need this calculation anymore. So to create a little bit of space, I'm just going to erase it. So there it is, it's gone. Coming back and looking at this situation, remember what we want to do is get an appreciation of how physics applies to bodies on an inclined plane. We've got two components, one component parallel to the plane here and another component which is at right angles to the plane. Now I'm going to call this component at right angles the reaction component, not because the component itself is the reaction, but it's going to lead to a reaction force because this component pulls the mass onto the plane, and so there's going to be a reaction force which is the plane pushing upwards, which is opposite in direction to this reaction component. And I'm going to call this component over here the sliding component. Now, we can express theta in terms of the sine and the cosine of theta as follows. The sine of theta is equal to opposite, which is the sliding component, divided by W. Okay? The cosine of theta is equal to the adjacent side, which is the reaction component, divided by W. And from these two statements, what we can get is the following. That the sliding component is equal to W sine theta, and the reaction component is equal to W cosine of theta. And we're going to use these very often when we see questions which involve an inclined plane. And like I tend to do, so that you make sure that you understand it correctly and there's less chance of you getting these kinds of questions wrong, we'll always want to go to first principles as opposed to just blindly applying a relationship. But in this kind of setup, what we have is that the force which pulls the mass down the plane, which is the sliding component over here, is W sine theta, and the force which pulls the mass into the plane, which is the reaction component, is given by W cosine of theta. So if we were to go back to our free body diagram, then on our free body diagram, what we can do is we can draw two forces, one which is the sliding component and the other which is the reaction component. And then we can label them, your sliding component being W sine theta, and your reaction component, which pulls this mass down into the plane, being W cosine of theta. So you'll see straight away that with a force which is acting this way, if this is a smooth plane without friction, this will begin to slide that way. So this sliding component, which is W sine theta, is going to govern the acceleration of this body down the plane. And W cosine of theta, which pulls this mass into the plane, is going to determine the size of the force which the plane exerts on the mass. And this force which the plane exerts on the mass, which is the actual reaction force, will always be equal to W cosine of theta, because that's what planes do. When you push into a plane, it pushes up with a force which is equal to the force that you are pushing down with, as long as that plane is not compromised. In order to explain that, just think of yourself right now. You're probably sitting on a chair. If you lift your feet off the floor, you are exerting a downward force, okay, which is similar to W cosine of theta, on the chair, which is a plane, and luckily it's not inclined, so you just exerting that downward force, there's no risk of sliding, and the chair is going to exert an upward force, which is equal to that downward force. And that points to a Newtonian action-reaction pair, which we aren't covering in this video, but I'm sure you'll find familiar.